All right, today we're going to play detective. We're going to solve a mystery that's hidden deep inside one of the most common materials in the world, steel. And our biggest clue? Well, it looks a whole lot like a chocolate chip cookie. Let's get into it.
So here's the central puzzle. Especially if you're, say, building a car, you need materials that are strong enough to keep you safe in a crash, but they also have to be soft enough to get stamped into all those complex curves of a car door or a fender. And on top of all that, they have to be lightweight. It feels like a total contradiction, doesn't it? Usually, strong stuff is brittle and soft stuff is weak, so how in the world do you get the best of both?
Well, the answer is this amazing stuff called dual-phase steel. And seriously, the best way to picture it is a chocolate chip cookie. You've got the soft, easy-to-shape cookie dough in the seal that's called ferrite. And then scattered all through it, you've got these hard, strong chocolate chips. Those are tiny islands of a super hard structure called martensite. That combination is what gives the steel its almost magical properties.
And look, this isn't just some weird science experiment. This stuff is a huge deal. This new kind of steel became the secret sauce that let carmakers build way stronger, safer cars that were also lighter, which means better fuel efficiency. It was an absolute game changer for the industry.
So what are its superpowers? Why is it such a game changer? Well, for one, it's incredibly strong, but also easy to form into complex shapes without tearing. And a big reason for that is something called a high-strain hardening coefficient. That's a bit of a mouthful, right? All it means is that the more you bend and shape it, the stronger it actually gets. How cool is that?
But you know, scientists, just making the steel wasn't good enough. They had to understand exactly how it worked under pressure so they could predict what it would do and, design even better versions down the line. And this is where our mystery really begins. It's a showdown between two competing theories.
Okay, so we've got two main suspects in our case. On one side, you've got Maleko's theory. Let's call this the simple suspect. It's really straightforward. It just assumes that when you stretch the steel, both the soft cookie dough and the hard chocolate chips stretch by the exact same amount, all nice and even. But then you have Tomoda's theory, our general detective. This one's a bit more nuanced. It allows for the possibility that the soft and hard bits might stretch differently. So the big question is, which one's right? All right, so the investigation is on. What's the first step? Well, the scientists took these two theories and decided to test them against data they already had from older, more conventional dual-phase steels. They just wanted to see which theory was better at predicting what was actually happening.
And this is where we get our first big twist in the case. You're not going to believe this. When they ran the numbers, both models worked. The simple one and the complex one. They both gave pretty much the same correct predictions for those older steels. The simple suspect seemed to be perfectly fine.
So you're probably thinking, wait a minute, if the simple model works, why bother with the more complicated one? Case closed, right? Well, hold on. Not so fast. Any good detective knows you can't just jump to the first easy conclusion.
See, here's the thing. The only reason the simple model worked is because in those specific older steels, the hard and soft parts just so happened to stretch by almost the same amount. Its main assumption was true purely by coincidence. It was like a suspect with a lucky alibi. To really crack this case, they needed a much tougher test. And that meant they had to set a trap. They decided to create a brand new, custom-built steel specifically designed to expose the truth and break one of these models. This was the master plan, the high silicon experiment.
So what was the recipe for this special steel? Well, they started with a basic low-carbon steel and added a key ingredient, about 2% silicon. Why? The whole point was to exaggerate the difference between the hard and soft parts, making the cookie dough even softer and the chocolate chips even harder. They wanted to create a situation the simple model just couldn't explain away. Now, the process to make it was pretty intense. First, they heated it up like super hot, over 920 degrees Celsius, to completely reset its internal structure. Then, bam, they plunged it into a freezing cold, agitated ice bath. This crazy temperature shock is what creates those super hard martensite chocolate chips. After that, they checked their work under a powerful electron microscope to make sure the structure was perfect for the test. Okay, so now they have their custom-made steel. This is it, the moment of truth. It was time to put this new material under stress and see, once and for all, what would happen. This was the final piece of evidence they needed to solve the mystery. So this is the million-dollar question. What happened when they started pulling on this new, high-tech steel? Would everything stretch together nice and evenly, just like the simple model predicted, or was something totally different going to happen?
And the answer was not even close. It was a blowout. The soft ferrite, the cookie dough, it stretched like crazy. But the hard martensite, the chocolate chips, they barely moved at all. The stretching was completely lopsided, totally unequal.
And just like that, this simple suspect's alibi was shattered. Maliko's model was built entirely on this one single assumption of equal strain. This experiment proved, without a shadow of a doubt, that for an advanced steel like this, that assumption is just fundamentally wrong.
So let's look at the final scoreboard. Maliko's simple theory, it completely missed the mark, way overestimating how the steel would perform. A total failure. But Tomoda's more general theory, our general detective, it was dead on. It matched the real-world data perfectly. Case closed. We had our winner.
And hey, don't just take my word for it. The researchers themselves summed it up best. They said that Tomoda's theory gives good agreement with the data, and most importantly, it reflects a more general applicability. In other words, it's the robust, reliable tool they were looking for all along. So what's the big takeaway from our whole steel detective story? It's that progress, real progress, often depends on finding the right model to understand a problem. A simple explanation might seem good enough for a while, but to really innovate, you need a model that actually captures the complexity of what's really going on.
And that kind of makes you wonder, right? We just peeled back the layers on a piece of steel. What other everyday materials, from the plastic in your phone to the concrete in our sidewalks, are hiding their own scientific dramas just waiting to be discovered? Something to think about. Thanks for joining me for this one.